it.
Yes, now am I audible?
Yes, sir.
Okay. Sorry for the delay. There was some network issue. So
no problem, sir. No problem. No problem. Yeah.
Okay.
Yeah. So shall we start, sir?
Yes.
Yeah. So welcome all the participants in the third day of a short-term training program. So today we have with us Professor Das Gupta, sir. So on behalf of Civil Engineering Department, I welcome Das Gupta, sir, and all the participants. Sir is currently working at IIT Guwahati as Associate Professor. He has done his MTech and PhD from IIT Kanpur with specialization in structural engineering, and also got the opportunity to do his postdoc from University of Togo, Japan. He has received many awards including ACI and IAEE, etc. With this, I will hand over the proceeding to Dr. Kaustubh Dasgupta, sir, and I request all the participants to kindly mute their microphones. Thank you, sir, and you may start, sir, now.
Thank you, Vipin, for the warm introduction. So, just a corrigendum that I was awarded the fellowship for doing postdoctoral study in University of Tokyo, but at the same time, I got the offer for faculty position at IIT Guwahati, so I did not join there. Okay. So anyway, so thank you. Let me share the entire screen so that I can show you the presentation. Is the screen visible now? Vipin?
Yes, sir, it is visible.
Yes, it is visible. Okay.
Yes, sir. Sir, you just hide that notification, otherwise it comes on the screen also, so it interrupts kind of.
Now it's okay?
Hides your things.
Now it's okay?
Yeah, sir, it is okay.
Okay, fine. So, good afternoon to all of you. And the topic of today's presentation is capacity design concept in earthquake engineering. Okay. So, some of you may be familiar, and for some of you, it's a totally new terminology. Okay. Anyway, we'll start with the basic and try to build up and see what exactly it means and how do we really implement that in earthquake resistant design or earthquake engineering domain, right? So this is the overview of the topics which I'm going to deal with. First, we'll introduce with what exactly is an earthquake and what are the effects. Then we will recapitulate some of the basic principles of the conventional structural design, and then see that how do we move into the earthquake resistant design philosophy, and finally culminate in the capacity design procedure. Okay. And then how do we implement this capacity design procedure in realistic design of buildings? I'll particularly focus on buildings, but in general it is applicable for any structure for which earthquake resistant design needs to be done. Okay. And then we will finally close with one or two of the major salient points. So as part of the introduction, let us recall that what exactly happens during an earthquake. So as you can see, there is the rupture of fault at some deep location in the Earth's crust, which gives rise to release of seismic energy. Okay, that seismic energy was originally stored in the form of strains and deformations in the rocky mass. Okay, once the energy gets released, waves start propagating in different directions, as shown along the two paths, the red and the green curved arrows. Okay, so along different directions, the seismic waves propagate, and finally they reach the ground surface. So initially they pass through the rocky mass. This is the rocky mass, and then they enter the ground layers, okay, the soil layers. And as you move towards the ground surface, they undergo all the mechanisms which are described in the physics of waves. Okay, so all those phenomena are undergone by those waves, giving rise to different wave fronts. And then finally, when they reach the ground surface, they propagate primarily as surface waves, as you can see here, the wavy lines, the wavy arrows. Okay, and these surface waves are the most damaging ones from structural engineering point of view. As you can see, the foundation of the building first interacts with the waves along with the underlying soil. That vibration gets propagated into the superstructure, that is the part of the building what we see around. Okay, and once this entire system undergoes vibration, so we get the soil structure foundation interaction and all those effects. Okay, so surface waves are the damaging ones, and our earthquake resistant design primarily deals with the effects of the surface waves. We also have the body waves, which started propagating after the rupture of the fault and after the release of the energy. However, those body waves, they are not so much damaging to the structural point of view. Okay, fine. So this is how the earthquake happens, and the waves come and shake up the entire structure. So depending on the intensity of ground shaking under the surface waves, we can have different levels of damages, minor damage to severe damage, and the well-known implications. Okay, so having gone through these effects of earthquake, let us see some of the visual effects what we generally look around. So most of you are familiar with these, but let us recall that what are the different effects. So from structural engineering point of view, the collapse of buildings under severe shaking, that is the primary concern. How do we prevent the entire collapse of the building? As we will see in earthquake resistant design, sometimes we allow the building to undergo damage. Okay, it's not that your building will be entirely damage proof or distress proof during the earthquake shaking. It's not like that. Okay, otherwise it will not be an engineering structure. The economy will not be coming into the picture. Okay. Anyway, so how to prevent such types of collapses is our primary concern. So this was taken from one of the building locations during Bhuj earthquake. As you all know that the open ground story buildings were the most damaged ones during the Bhuj earthquake shaking, and this was one of the building collapses in Ahmedabad city. Okay, so as you can see, a lot of infrastructure gets damaged. Okay. Next, we move on to the bridge type of structures, or which are used in transportation engineering. Okay, so this is a spectacular collapse of an elevated expressway in the city of Kobe. Okay, so in 1995, a major earthquake happened around the Kobe city, also known as Great Hanshin earthquake. Okay, and as you all know, the country of Japan has been pioneer in developing earthquake resistant technologies as well as different engineering guidelines. However, at that point of time, their level of knowledge somehow proved to be deficient, especially when these types of collapses were observed. Okay, there were different reasons for the collapse, as I had mentioned: interaction with the soil, possibly some deficiencies in the design, understanding of the mechanism. So many reasons and many factors were behind this collapse. Okay. Anyway, we'll not go into that. So as you can see, this expressway collapse also brings a major loss to the critical facility. What is critical facility? These bridges are very helpful in mobilization of relief, mobilization of rescue work, okay, mobilization of injured people, health people to different remote areas affected by the earthquake. So if such bridges and flyovers get collapsed, there is no way such rescue and relief operations can be undertaken. Okay, so these are called critical facilities or critical structures, such bridges, flyovers like that. So in no way any point of time, they should be allowed to collapse. They should be always in functional condition, whether there is earthquake, whether there is no earthquake, whatever be the condition. Okay. Let us move to the next one. This is a figure from Navalakhi port along the coastline of Kutch region in Gujarat. Okay. So that port area had this railway line running along the embankment along the coast. And then what happened? There was severe movement of the ground during the shaking. Those waves, surface waves, called severe ground deformations, ground displacements. And then, as we can see, the levels and the different reference points all have become topsy-turvy. The signal has undergone this tilting, as well as the railway track has become undulated. So in no way these are in functional condition. Again, the same issue, if your railway track is damaged, your transportation of goods, wagons gets disrupted, and you cannot mobilize the relief and rescue missions. One of the funny visuals, as I will say, that how can a manhole come up during an earthquake, right? This was in 2004 around the city of Niigata in Japan. This Chuetsu earthquake took place. So there, what happened at many locations, this is one such location, you can see that this manhole just beside the side of the road on this pavement was actually had the cover at the pavement level, ground surface. And then during earthquake shaking, it came up. Okay, now it is standing nicely above the pavement level. So what happened was the soil below this manhole or around the manhole, so that got almost liquefied. Okay, so the soil lost its shear strength, right? And then it was behaving almost close to liquid-like condition. Okay, so in that condition, the manhole became a floating object, and it came up, right? And when the earthquake went away, the soil regained its strength, but the deformation and the movement of the ground was permanent, and the manhole sat nicely after the earthquake. Okay, so apparently this is not causing an injury, casualty, financial loss. No, it's not like that. But again, what's the implication? This manhole was supposed to carry out some functional purpose, right? This was built. So obviously that is disrupted. So whether it's connected through sewerage line or whatever, right now it's not in functional condition. When you open the manhole cover and allow the rainwater to drain off in the underlying pipes, so that cannot be done by this manhole. There were many earth dams around the region of Kutch in Gujarat, and a few of them got damaged. Now, earth dam is very important, especially in dry, arid regions where the water retention is a major issue. So, if your earth dam gets cracked, you will have the water percolating out, and the retained water is lost. So, obviously, that causes misery to the villages and all the people, cattle, and everybody. So this was also a major infrastructure damage, because at that point of time it was very difficult and costly to rebuild and possibly repair this earth dam. It's very difficult. You have to bring the soil compact and all those things carry out. So as we have seen, different uh, regimes of infrastructure undergo different types of damages, and the implications and the consequences are manifold. Okay. Primarily, what we look at are the physical damages we see around visually, and the associated economic damages. Okay. So we know that depending on the magnitude of earthquake, depending on the location of the site, we can have different degrees of damages. So anyway, our society is not supposed to bear and see these damages, right? It is not a direct impact, but social impact is an indirect consequence. Okay? Because many people have their livelihoods getting affected, right? So that leaves definitely a social impact on the future of especially daily wage earners and other people. Okay? So it's not a direct consequence, but still it has a lasting effect. All these make it imperative to focus and carry out earthquake resistant design. So we never forget to highlight the importance of such issue. So moving on, let us relook at what exactly does conventional structural design say. Okay, how do we carry out the design of general buildings? So before we embark on the design, we have to first analyze the structure, and nowadays most of the analysis is carried out with the help of computer programs with different graphic user interface or with the help of different background programs. So first of all, we have to idealize the realistic building and model it in a possible way so as to capture the real behavior. Okay. So how do we model the building? That is the conventional way. All your beams and the columns, as we can see, this is a typical reinforced concrete frame building, what we see around in urban areas. Okay. So most of the time we model the beams and the columns. We may or may not model the floor slabs and the roof slab. Okay. And we never model the soil, underlying soil over which the building is standing. Okay. What is the reason? Because behavior of soil is more uncertain than the behavior of concrete and steel in the building. Okay. So unless you are certain to a particular degree that how your material will behave, okay, you never incorporate it in your design. That's why you look at the design guidelines or the design codes of all the countries throughout the world. Nowhere it talks about taking the soil model into consideration while analyzing the building for its design. Okay. So that is the main reason. And if you map this same philosophy into the dynamic behavior regime of structure, your dynamics in of this system will involve soil structure interaction. Okay, in what I had mentioned that. So in soil structure interaction also, you will never find any provision, any clause in any of those design guidelines. Okay, that is the main reason. Fine. So as you can see at the bottom of the columns of your idealized building frame, we always restrain the degrees of freedom. This notation with these hatched lines, okay, that represents that all the translational and rotational degrees of freedom about the axis, they are all restrained. That is the most simplistic way. To some extent, it's a conservative way also to get the estimate of design forces and moments. Okay, so that way it is fine, right? So this is how you model a building frame in conventional design. Okay. Your behavior of material is mixed type. Why am I saying mixed type? Is when you do the design, you take the material stress strain curve in a non-linear way so that it's not linear elastic. Okay. But at the same time, when you do the analysis, when you ask the computer program to carry out the analysis, you do the analysis using a single modulus of elasticity for either reinforcement or concrete. Okay. That means your modulus of elasticity does not change. It incorporates linear elastic behavior. So your analysis has the implication of linear elastic behavior. However, while doing the design, you use a stress strain curve which is non-linear, which is not a straight line. Okay, so that's why I mentioned mixed. So there is an inherent contradiction in the underlying statement that you use non-linear material stress strain curve and linear elastic behavior. Okay. However, we'll not go into that debate. Why has it been prescribed like that or so on? Okay. So your frame members, okay, which are like linear elements. So they are assigned linear elastic properties depending on the grade of concrete, grade of reinforcement, whatever be the situation. Okay. So to analyze linear elastic behavior, we assign the design loads, the self weight of the building, your live load at different floors, that is the weight of the movement of the people or of goods, whatever. And then you have additional loads coming from wind, earthquake. If it is in a cold region, you may have snowfall and so on. So all those possible loads are considered. And when we are considering in analysis for particularly with earthquake loads, then we have to refer to the design load combination mentioned in the Indian standard IS 1893 2016. I forgot to mention the part. This is part 1 for buildings, but then there are other parts of IS 1893 also, right? So part 1 is for the building, and as you can see here, for each of the elements, this is a frame building with reinforced concrete wall. So what you do, you isolate each member, and from the computer program itself, you get the design forces and moments. Basically, uh, it solves the entire frame or the entire structure using finite element method, and then gives you the internal forces or internal moments at the different sections. Okay. So if you draw the free body diagrams, you should also arrive at the equilibrium condition. Okay. So based on these design forces and moments, then you do the design as per the limit state method. So as we know, the limit state method has two parts. One is the limit state of collapse, which deals with the strength of your member, how much bending moment the beam can take, how much shear force the beam can take or the column can take before it collapses. Okay, so that is also the limiting strength or the ultimate strength, and we talk about the capacity, right? Design capacity. So primarily your members in the building are designed against flexure and shear, that is the bending and the shear behavior. So depending on the geometry, whether the members are slender, whether they are short or squat members, you'll have dominating effect of either bending or shear. And your prescriptions or the provisions of the relevant Indian standard, if you're looking at the Indian context of building design, these are mentioned here. So most of you are familiar with these. Depending on the element what you are doing, if you are looking at piles, you may have to refer to the different parts of IS 2911, okay, for the relevant provisions. But primarily, your reinforced concrete sections and the components, they are designed as per these guidelines. Okay, and then you do the reinforcement detailing also as per the handbook SP34. Then you move on to the limit state of serviceability. So primarily you check the section size and the basic details, whether they are able to carry the bending moment or force from the strength point of view. And then you also see that under the different load conditions, what can be the maximum deflection, how much the building can sway under wind or earthquake, or it can settle down, whatever be the criteria. Okay. So that entails under the limit state of serviceability. So having done all these, the primary purpose of the conventional design is to first fix the section dimensions, because the material properties are already mentioned. Once you are going for a building, the owner or the client will not go beyond a certain grade of concrete because it will incorporate cost, availability of raw materials or so. And more or less your geometry of the building, the configuration, that is also finalized from the client and architect, that mutual point of view. So the structural engineering is basically assigned to get the preliminary section dimensions, and at the same time checking the safety and serviceability for the design level behavior. Okay, so once we talk about design level behavior, okay, so you have to do the analysis as I mentioned earlier to get that bending moment, shear force, axial force, all the stress resultants for the design force or design loading condition. So there are two aspects in the Indian standard or any other standard. One is how much the level of the force or moment coming in the section of the member from the applied loading, that gives you the design level force or moment demand. Why do we use the term demand? Because the force of the moment at a certain section of a beam, at a certain section of a column, whatever will be coming after externally applying the loads, right? So that means the loads are demanding how much force it wants at the section of the beam. So that is the demand imposed by the external loading from the structure itself. So the structure is subjected to that much demand from the external loading. That's why we use the term demand in these situations. Okay? On the other hand, your structure has certain dimensions, it has a certain capacity, how much it can take. Beyond that, if you still load the section, it will collapse, it will rupture. Okay, so every structure, every section, every beam, every column, every pile has a certain capacity, maximum moment what it can take. So these are the two aspects. So when you're looking at the moment demand, we look at the code prescribed load factors. So load factors are given by this gamma F. Okay, so here we get the design level force demand FD subscripted with D. Okay, and then we have the characteristic force F multiplied by the load factor. So the design load is obtained by enhancing or magnifying the characteristic load by the load factor. So these load factors are prescribed by the course. On the capacity side, do we use the actual material properties? How much is the yield strength? How much is the ultimate strength? How much is the rupture strength? Do we use them? No, because we don't want the material to go up to that extent. We don't want the material to undergo any type of small distress. Okay, so that's why we divide the actual strength of material by again a factor of safety. Also, we call that as partial safety factors. So these are also prescribed by the code. Okay, so partial safety factor is prescribed by the code, and this is given by gamma m. So the subscript m stands for the material point of view. So we have the characteristic strength divided by the partial safety factor. So in conventional design, depending on the country where you are going to design the structure, which guideline you are going to follow, this gamma F, gamma M are specified. You are not going to play around with them. Okay. So nowhere or at no point of time during the entire conventional design procedure, you are going to use the actual material behavior. Okay. There is also another reason why don't we use the material behavior, because the level of uncertainty is always there. If you carry out some concrete mixing and try to get a compressive strength for the characteristic tube strength as 25 MPa, you carry out this mixing on 7 consecutive days with the same set of raw materials. You will never get the same values on any of the 2 successive days or what. So always you get around 25. So some may give you 25.3, 25.7, some may give you 24.6. So around 25 you will get that, right? So that uncertainty is always there. So we never try to fix or do the design calculation based on the exact actual material strength, because we never know what exactly is going to be the value. So we keep a sufficient margin safety so that we are on the conservative side. So since actual behavior is not considered, at some point of time we will see that we are not doing justice, especially when we are trying to do the design for resisting the earthquake effect. So in earthquake resistant design, it has 2 levels. One is the conventional design as per the limit state of method, strength and serviceability, collapse and serviceability. And the second stage is given by the capacity design. Okay, so that's how in earthquake resistant design, capacity design is one part. Okay, so when we talk about earthquake resistant design, it's not only capacity design. You have the conventional structural design in place. At first place, you have to do it. No option, no other way. And then you have to do the capacity design in order to ensure your safety against earthquake shaking, right? So this is how your capacity design becomes mandatory in the entire earthquake resistant design procedure. So in capacity design, as we will see, the actual material behavior is considered. Okay. So let us briefly dwell upon the basic philosophy of the earthquake resistant design. Okay. So before we go to the earthquake resistant design, another term which many of you may be hearing or may be confused that what exactly is the difference with earthquake resistant design. That term is earthquake proof design, right? So it basically talks about an undamaged structure. Whatever be the level of shaking, okay, the structure will not be damaged at any point. Okay, at low structure will never of any damage. Now, what is damage? Under normal circumstances, we see that your beam or column or any concrete surface or concrete member has small cracks, micro cracks, okay, which may be observable in naked eye, which may not be observable in naked eye. And also you have many cracks in the inside or the interior mass of the concrete, which we can't observe from the outside. Okay, so these cracks make the concrete weak, right? Any type of crack make the section or the object weak. Okay, so is this a damage? In structurally, the micro cracks are not the part of the damage. Okay, only under the application of load, right? When under the application of load, your cracks start propagating, cracks are formed, and they are going to have a detrimental effect on the behavior of your member, then only we term them as damaging cracks, or those cracks are part of the damage, structural damage. Okay, because you take any concrete section of any size, cube, any shape of the object, you cast it, allow it to cure, get hardened for the required minimum 28 days. Even with accelerated hardening admixture, you can get the almost the same strength in 7 to 10 days. Whatever procedure you follow, you can never avoid those micro cracks. They are inherent uh, part or the characteristics of your concrete. So they are not the damaging cracks. So in earthquake proof design, you will see the micro cracks. But whatever be the earthquake shaking, whatever be the loading, these damaging cracks or under the application of load, no crack will be formed. Right? Now, that involves very high construction cost. If you want to design any column of a building under such condition, you will land up with an enormous size, which is not practically feasible. Right? So that's why earthquake proof design is never carried out. Okay, especially for ordinary buildings. But if you look at the entire domain of the structures, yes, some of the special components of certain industries or so, they may require such earthquake proof design. Suppose you have a tank which is primarily intended to retain certain chemicals, liquids, okay, and which are never expected to spill out or leak out. Okay, so those tanks, if they are made of concrete, whether reinforced concrete, pre-stressed concrete, they should never undergo such damaging cracks. Whether there is earthquake, any type of load, natural hazard, whatever you talk about. Okay. So under that circumstances, the design will have that earthquake proof term, right? But those are rare special cases. We are not going to consider them. Okay, they require special guidelines and other analysis. Okay? You may have to do very detailed analysis to ensure that. So for ordinary structures, we always carry out earthquake resistant design, where we are going to have selective damages, right? Selective damage at certain locations. Okay, and that brings down the construction cost, that brings down the sizes, and makes it affordable for ordinary people. So for earthquake resistant design to be carried out, we need to know the level of shaking, right? You have a building which is located at some site, and then you have different locations of faults, okay, or geological features around the site. Some of them may be within 10 to 15 kilometers, some of them may be 50 kilometers, some of them may be 700 kilometers. Okay? Now the question is, which are the faults, okay, going to give you the maximum possible shaking for the building at that site. Okay? That is the primary concern. And till now, it has not been possible to very accurately determine and very deterministically state that yes, this is the maximum possible ground motion which is going to be experienced at this site. Till now, people have not been able to find out that. Okay? So we generally talk about different levels of shaking, and most of the design philosophies are based on 3 levels of shaking. As you can see here, one is the minor shaking, one is the moderate shaking, and third one is the strong shaking. Okay. Now, it's very obvious that if the shaking is minor, very less vibration, your damages are minimal. Okay. And if you have very strong shaking, you have the possibility of collapse. But then we also look at that how frequent such earthquakes, which will give to minor shaking, are being experienced at that site. Okay. How frequent are earthquakes which are giving rise to this strong shaking, okay, strong shaking, very damaging shaking, are experienced at that site. So there are 2 levels. If you see the statistics or the return period of different earthquakes, which are causing different levels of shaking, the earthquakes which cause minor shaking, they have less return period. That means they are going to occur more frequently. Earthquakes which are more damaging, high magnitude, extensive shaking, they are going to occur less frequently. Okay, maybe once in 50 years, once in 100 years, once in 300 years, you never know, right? So whenever we try to establish the level of design loads for earthquakes, we have to consider the return period or the frequency of occurrence of the earthquake. So generally, if you look at the guidelines, we don't do any separate statistical analysis for that. Okay, already the codal guidelines give us that for this level of return period, this is the level of earthquake load what you're going to experience. Okay, all the structures, not only buildings, they are designed for a service life. So I guess most of you are familiar. A building may have a service life of 70 years, 80 years, at the most 100 years, not more than 100 years, 80 to 90 years, maybe maximum. Beyond that, we expect that the building should be demolished and a new structure should come up that place. So within that service life of that building, how frequently this minor shaking will be experienced, how frequently this strong shaking will be experienced. So these are the questions people are concerned with. Okay. So as you can see on the right hand side, as you have more damaging earthquakes, right, the frequency is going to be changing according to that. Okay. So this is how your levels of earthquake shaking are going to happen. So now let us look at one of the fundamental difference in the behavior or the nature of the problem when you have earthquake resistant design and wind design. Okay, why I wanted to clarify this, although it may be slightly out of context, but since many of your students, so I would like to clarify that the basic nature of the application of force itself is different. Okay, many times when we ask questions in interview or so, we see that the application of load is not clear to most of you, how the load is applied on the structure. Okay. When you look at the earthquake, it primarily comes from those shaking of from the surface waves passing through the rock and then soil and then shaking the foundation. So it's primarily the ground deformation. The ground is moving. It's not that we are applying externally some force or trying to push the building. No, it's not like that. Whereas in case of wind, we have the wind speed in different directions at different points of time, making it a dynamic pressure from different directions. Okay, so there no deformation or no movement of the ground is involved, the underlying foundation is involved, but it's only application of lateral forces. Okay, so the deformation or the behavior of the building is completely different from the original source part, because the deforming foundation is going to shake up the building for earthquake, whereas in case of wind, the deformations are directly coming from the force application or pressure application, right? So due to this difference in the application of force on the building, the two behaviors require two different characteristics. So if you take a small frame, very small idealized frame, okay, consisting of two columns and there are two levels, so two beams or two slabs, and you apply the force, okay, and then once you apply the force, it tries to sway, and that involves a top level displacement of delta, okay, at the top. So in case of this variation of h with delta, if you look at the curve, so you get a generic curves like this. And in case of wind, when you are applying the pressure directly, the wind behavior is mostly in the linear elastic range, right? Unless you are looking at very high intensity gust during cyclonic or tornado condition, then you can have severe damage. Otherwise, it is linear elastic behavior, no damage is involved. Okay, so this wind behavior is mostly elastic. However, during the ground deformation, shaking of the bottom, when your frame is expected to deform, your lateral load behavior is going to involve a large range of deformation. Okay, it should span over a large range of lateral deformation. So your building should be able to withstand the sway to a large extent, whichever direction. Okay, so that brings the inelastic behavior into action. Under that large deformation, your building will not be able to uh, extend its linear elastic behavior. It has to go into the inelastic or non-linear range. So this red part, as you can see, that tries to cover the large deformability, and that brings the inelastic behavior of the different members of the sections. Okay, so behavior wise also, the two applications of the ground deformations in earthquake and the dynamic pressures in the wind, okay, they bring different effects. Okay, so in order to understand in a slightly different aspect, the loading in case of earthquake is from ground deformation. As you can see, this is the general signature of the variation of displacement or velocity or acceleration of the ground shaking with time. Okay, so this involves the displacement loading on the foundation. So basically, we are applying displacement on the piles, displacement on the footing. Okay, we are not applying pressure on the beams and all. Whereas here, as you have mentioned, is direct application of the pressure on the building. Okay. Now, some of you may be asking that we also look at a similar distribution of lateral forces in case of earthquake analysis. When you do the equivalent static method of analysis as per IS 1893 part 1, we also look at a diagram in somewhat similar way in case of earthquake also. So how does it arise? When we are saying that it is primarily due to ground deformation, but then when we really apply the seismic load, we have the different loads at the different floor levels. So how do we really reconcile on these two? So what happens is this dynamic shaking of the ground, this deformation time history or the deformation signature of the ground is imposed on the foundation. It gets propagated to the top, the superstructure, the building. And then what happens when at different levels where masses are lumped in case of a multi-story building, we have the inertia forces coming into action. Okay, so the different levels of the lateral force application, what you have seen these type of figure in case of application of lateral forces, earthquake loading, are nothing but the inertia forces which are generated at the different levels of lumped masses. At the floor levels where we have the slabs, we have the different masses lumped. So they are going to give rise to those inertia forces. Okay, so those forces are applied on the building, right? So what we are doing, we convert this ground deformation into equivalent lateral forces and apply them on the building for finding out the design forces and moments in case of earthquakes. Okay, so please don't get confused. This is the direct application of wind pressure on the building, and in case of earthquake, we convert the ground deformation into the inertia forces. Okay, so that conversion gives us a simplistic way of calculating the design force and moments. The analysis becomes much more simplified. So we have the force control system where you have the gravity loads under the self weight or under the wind, where you have the failure occur if the imposed load is more than the yield force. Why is it so? Because under gravity load, that is self weight, under live load, under wind, we do not expect any damage to occur. Linear elastic behavior. So we have the yield point, yield level in your entire nonlinear behavior, nonlinear curve. Okay, so beyond this yield point, you never expect the structure to cross. Okay, so that's why your system is a force controlled system under self weight or live load like that. Whereas in case of earthquake loads, it is displacement controlled system, because as we have mentioned, we need large deformability. If you look at the figure, you have the large deformability or the displacement. So imposed displacement, if it is more than the yield displacement, still we do not call it as a failure. Okay. So that is the fundamental difference between your force control system and displacement control system. So the main characteristic which we require for such displacement control system is your ductility. Okay. The system should be ductile. Okay. So in earthquake resistant design, time and again we are also going to emphasize in the next slides that ductility is the key for a desirable behavior. So what exactly is ductility? So whenever we ask anybody what is ductility, we get different types of answers. Okay, primarily in case of seismic behavior, earthquake resistant design, what we look at is your large extent of inelastic deformability, right? The inelastic deformation capacity will be large, right? With the condition, with a certain flag. What is the condition? Your strength should not reduce. So as you can see here, this blue dotted line, first it was in the linear elastic behavior, then it picks up strength with a reduced slope. That means the stiffness has reduced, certain damages have started occurring, and then it reaches at some point. Had it been a brittle failure, it would not have gone up to such a large deformation. It would have already dropped its strength much earlier. Okay? So this degradation of strength or reduction of strength at low level of deformation is a no, not at all desirable. Okay, strictly no. So it cannot, a system cannot be a ductile system if that degradation of the strength is observed. It has to maintain the level of strength, right? Even at large extent of the inelastic deformation. Okay? So there are different exact definitions that how much strength degradation is allowed when you call a system as ductile, but primarily the strength degradation should be minimal. Okay? Then only we call the system as ductile. It should not be like it picks up the strength and drops off and then you call it a ductile system. And then when we try to mobilize ductility through the design procedure, we are having the building with so many components and so many sections that the ductility also needs to be sufficient at different levels. So basically different measures of ductility are there depending on the location. One is the overall structural ductility. Then if you go back to the previous figure, here we were looking at this idealized small frame where we had the total lateral force H and the lateral deformation delta. So we were looking at the overall behavior. This graph shows the overall behavior of the frame. Okay, so the overall structural ductility should be sufficient. Story ductility. What is story ductility? You take any story and you know the shear force at the bottom section of the column. You add them up, all the bottom sections of the column. So at the bottom of this story, what is the total shear force? So total story shear versus the displacement of that story. So that will give you the story ductility. Similarly, we get member ductility. For each of these columns, each of these beams, you get the member ductility. Of course, you get the section ductility. So there are different measures of ductility. I'm not going to the detail, but when you'll be doing the earthquake resistant design, all these you need to keep in mind. So that's what we desire. So let us summarize the earthquake resistant design, the basic philosophy part, before moving on to the capacity design. So we expect damage. It cannot be earthquake proof, but the level of damage needs to be regulated along with the location. Okay. So as you can see from this wonderful figure, that your undamaged structure, when subjected to this shaking, gets damaged primarily in the masonry infill walls, as you can see from the cracks. Right now, your main columns or the main structural beams, they are undamaged. So the question is whether we will allow it, or whether we will call this behavior as the desired behavior or not. Your main structure is undamaged, but damages or energy dissipation has occurred at certain locations in your infill walls. Okay? So that way, for every structure, looking at the components, we have to select the location where you want the damage to occur. Okay? And then you have the necessity of the ductile behavior. That is utmost necessary. So when you looked at the overall behavior, the same thing, we want to re-emphasize that if you continue the linear elastic behavior, you get the maximum elastic force. Okay, no damage. So this is the level of the force you will get if you want earthquake proof design. Linear elastic behavior, no damage, no reduction in the stiffness, no reduction in the slope. Okay, so this linear elastic response will give you that earthquake proof behavior. But we are going to land up with large size of members because this F max is a large strength. So all your columns and members are going to have the total strength like this. So that will involve large sizes. Instead of that, we allow damages and then your slope gets reduced, and at the same time we have to trade off with a large deformability. So we want ductile response, but we don't want brittle response. So brittle response means your strength degradation is very high, and at very early deformation, the strength gets degraded. So brittle response is a strictly no. We want the ductile response. In order to have good earthquake resistant behavior, we also need to avoid certain types of nonlinear behavior. So some of you may be familiar that whenever we talk about nonlinear behavior in structural engineering, we are primarily dealing with two types of nonlinearity. One is the material nonlinearity, which involves this cracking of concrete, yielding of steel, crushing of mortar, crushing of concrete, like that. And there are other categories of nonlinearity, which is known as geometric nonlinearity, which deals with the deformed shape. So one of the very common example of a decremental geometric nonlinearity is buckling. Okay. The sudden lateral deformation under axial compression, okay, of any vertical member, so that is called buckling. Okay. So then you have the P delta effect, P capital delta, P small delta. So all these are geometric nonlinearities. Now, if you look at the effect of geometric nonlinearity on the behavior, most of the time, these geometric nonlinearities, if they tend to dominate the behavior, you are going to land up with a brittle type of behavior. It will not be a ductile behavior. Okay, so we need to strictly impose the criteria to avoid geometric nonlinearity. Okay, so premature failure needs to be avoided. If premature failure occurs, very early failure occurs, your building will not be able to take that deformation. Okay, not be able to take that sway. Before that itself, it is going to ding down. And encourage different types of material nonlinearities. Okay, why am I saying all material nonlinearities? Because in some way or the other, they help in the energy dissipation, right? So whatever seismic energy which is coming as input to your building from the shaking of your foundation, they need to get dissipated. Okay. Then only your proper behavior will be mobilized. So in that case, you need to determine which failure mode should occur first. Okay. Then your locations of inelastic action, then your moment resistant connections. So all those come under the detailing. Okay. When you do the detailing, whether it's reinforced concrete, timber structure, masonry structure, steel structure, whatever you talk about, detailing is very, very important. Okay. So these are the summarizing points for an earthquake resistant design. So as we had seen earlier, your capacity design is one part of earthquake resistant design. Okay, so we will move to the capacity design. Before that, if let us take a break for a couple of minutes. If you have any questions till now, let us interact. Any question?
So participants, if you have any question till now, you may ask.
So when we teach in class, when we address our students, if we do not see any question, that means either the entire stuff has been very well understood, okay, or it may not have been perceived or understood by anything, by anybody. Okay, so anyway, feel free, please feel free to ask any question. Okay? Others can also learn. Don't feel shy. I guess there are a number of students, right, Vipin?
Yes, sir. Yeah.
Okay, so let's move on.
Okay, sir.
So, having that background, since we have come across certain times terms like requirement of ductility, your selective damage at certain locations, these are all part of earthquake resistant design. How are these going to help in the capacity design? Okay, because capacity design is the second stage and the most important stage for earthquake resistant design. So let us start with the failure sequence. Okay, when we start with the failure sequence, we look at the strength hierarchy. Which component is going to undergo failure first? Okay. Whether it's slab, whether it's beam or column or footing or the soil, whichever. Okay. So in case of a reinforced concrete frame building, you have different components. Most of you are familiar. Okay. Just a minute. Yeah. So in an RC frame building, as you are familiar with the different components, the most secure ones where we do not expect the failure generally happening in case these are the slabs and the beams. Okay, because slabs are designed in such a way that it is very unlikely that slabs are going to fail. Although during certain earthquakes, slabs have been observed to undergo failure, but those are very rare. Then you have the beams. Okay, uh, beams are also not observed to undergo even failures. The next section, which have been observed to undergo failure and have more detrimental consequence on the overall behavior, is the column. Okay. It has serious consequence. Why? Because the columns are the vertical members on which all the components are supported. Right. So once these supports are going to go away, then obviously it will have a cascading effect.
Sir,
So wherever
hello.
at certain, yes,
Sir, sorry to interrupt. Sir, I just wanted to ask that while considering geometric non-linearity, so when do
yes,
we consider it in analysis? Like if we are analyzing any structure in software?
right. So uh, nowadays, most of the computer programs or the softwares which you use,
Yes.
they have one option that you can do the analysis with and without the P delta effect. Okay.
Okay.
Ha. So one of the types of geometric nonlinearity which is important is the P delta effect. So
Okay.
in P delta effect, what happens whenever you have any member having axial force as well
Yes.
as your lateral force, okay,
Yes.
the moment gets enhanced by the combined effect. Generally, the bending moment is contributed only by the lateral force. Okay.
Okay, sir.
So if you have a column, you have the vertical force and the lateral force. So generally at the bottom of the column, we try to get the base moment by only considering the lateral force. However,
Okay.
when under the lateral force your sway is large
Yes.
deformation, then your axial force also begins to contribute to the base moment. So under the
Okay.
combined axial and the vertical the lateral load, your base moment gets enhanced. So
Okay.
that is the P delta effect. So
Yes.
many computer programs have the option you can switch on or switch off the P delta effect. Okay.
Okay. Okay.
So now
So
in linear elastic analysis, what we do for
yes.
the design. Okay.
Yeah.
So linear elastic analysis is applicable when your displacements or the deformations are small,
Yes,
right?
sir.
Your linear elastic behavior, so the strains are small, right?
Yeah.
The yield strain has not reached, the inelastic
Yes.
or the plastic behavior has not started. So small strain, small deformation. The
Hmm.
building is also swaying to small levels of lateral displacement. Okay, so
Hmm.
if you have small lateral displacement, obviously the effect of the vertical load on the base moment will be less. So
Yes.
for linear elastic behavior, normally the P delta effect is almost negligible. So
Okay.
this option of switching on or switching off, considering or not considering P delta effect, is primarily associated with the nonlinear analysis.
Okay.
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 So I'll just mention nonlinear analysis briefly at one point of time. We have on the last lecture of this short-term course by Professor Hemant Kaushik on nonlinear analysis. So in nonlinear analysis, you expect large lateral displacement because you have the inelastic action. Your material nonlinearity is mobilized. You have inelastic action, so large strain, large displacement. You have the contribution of the P effect more. The vertical force contributes more. So
Okay.
those cases, whenever there is a possibility of failure, that gets aggravated if you consider the P delta effect. So the software, most of the software nowadays have the option of considering
Okay.
P delta effect.
Okay. Okay.
Apart from that, if you look at buckling, it is it is probably not considered in most of the softwares. What you need to do is you need to find out the axial forces in each member, column or beam, and then
Yes.
check the critical load separately, whether
Hmm.
it's that Euler buckling load or any critical buckling load, whatever measure you consider. So that needs to be checked separately.
Hmm. So, sir, one more thing, like while doing non-linear analysis, actually, for the some part of or some amount of load, structure is will still be linear, behaving linearly. So,
Right.
that P delta effect, does it consider in that part also or not?
Uh, it should consider for the entire structure.
Yes, sir.
Yes. Generally, it should consider for the entire structure.
Okay, sir. Okay.
Yes.
Sir,
So,
Nitin Sharma is asking, sir, during P delta, do we require diaphragm of structure?
diaphragm, diaphragm structure means that rigid diaphragm action, or which diaphragm you're talking about?
Nitin Sharma, you just unmute yourself and ask your question. Rigid, sir, he is saying rigid diaphragm.
Rigid diaphragm.
Yeah.
Yes. See, rigid diaphragm action is basically switched on to assign the in-plane stiffness of your floor slab, right? In-plane stiffness of the floor slab. So your reinforced concrete floor slabs are generally very stiff in its own plane. They don't bend. If you apply a lateral force on the floor, they will not bend like a beam. Only when perpendicular to the plane of the floor, if you apply a vertical force, it will bend like a beam. So the rigid diaphragm is basically tries to capture the in-plane stiffness of the floor slab. All the points on the floor are going to move in an equal amount, whichever direction you subject it. So even when you have P delta effect, you have nonlinearity, your rigid diaphragm action should be there. If you are having reinforced concrete floor slab, rigid diaphragm action should be there. Unless you are having the floor slab with lot of openings. In industrial buildings, we have floor slabs with lot of openings, cutouts to pass the ducts, pipes, cables, and various equipments. So when you have large amount of openings or gaps in the floor slab, your uh, in-plane stiffness becomes very less. So in some of the cases, if you apply the horizontal force on the floor slab, it may bend. Okay, so then it becomes flexible diaphragm. So those are exceptional cases. But in normal residential buildings, and where you have buildings or structures, continuous reinforced concrete slab without any cutout or opening, your rigid diaphragm action should be mobilized at all the time. Okay.
Okay, sir, you may continue now.
Okay. Fine. So when we look at the different components, we have the columns failure giving serious consequences. We have the failure of foundation. It is more serious because most of the times it's very difficult to find out how the foundation failed, because you have the surrounding soil, and then how exactly it vibrated and behaved during the earthquake shaking is very, very difficult to assert. Okay, but still people put sensors and instrument the entire building, starting right from the foundation, soil, and every time. So but still they have serious consequences. And obviously, as I mentioned, the modeling of soil is very uncertain, and the failure of soil is also very, very detrimental. Okay, you never know which part of the building gets settled down, or some part of the soil may get liquefied. So there are various possible effects. So once we have the strength hierarchy, and then you have the type of damage. So some of the failures are brittle in nature, some of the failures are ductile in nature, right? For example, in a steel frame building, if you look at the failure of the bracing, right? So as you can see here, these are the braces and these are your beams. So on the lateral load, what will happen? These braces will also have some axial force. Bracings are primarily detailed in such a way that the ends do not transfer any moments. So they are primarily like strut members or tie members, only carrying axial forces. Okay. So your failure of these braces can be in that buckling form. Okay, if they are under compression, if they are under tension, they can have tension yielding. So beams generally undergo frictional yielding. Okay, and then the beams can undergo local buckling also, like flange buckling, shear buckling, web buckling. There are different forms. So some of the brittle failure modes are possible, some of the ductile failure modes are possible. So again, if you plot the overall lateral force versus deformation profile, this curve, your desirable behavior is the ductile is in nature with flexural yield response, and your geometric nonlinearity in some form of buckling, whether it's global buckling or local buckling, it's non-ductile. That's why we mentioned to avoid geometric nonlinearity in one of the earlier slides. And brace failure, if it is in compression, okay, in the form of buckling, it should be avoided, because all these uh, buckling failures, they are premature, they are not contributing to the required deformation capacity. Okay? So these should be avoided. So the type of damage becomes important. So in the earlier slide, we talked about the hierarchy, which component will fail first. Okay, and next comes the type of damage. Now, in your superstructure, if you leave apart the foundation and the soil part, in your superstructure, the slabs are least likely to fail. So most of the time, our capacity design for reinforced concrete frame building revolves around the failure of beam and column. Okay, so you can have two possible configurations of the building. Okay, under the same design load, you can have different configurations. So the sizes what you choose for the beams and the columns will give rise to one possibility where your column is comparatively weaker as compared to the beam, right? The second one has the beam comparatively weaker as compared to the column. So one is called weak column, strong beam, because as you can see, the beams are having more depth as compared to the lateral dimensions of the column. And the other one has the weak beam, strong. Now, as we mentioned in the strength hierarchy slide, your failure of columns is detrimental as compared to the failure of beams, because they are the main supporting vertical members. So here, your beam is stronger as compared to column. So the weak columns are most likely to fail earlier under the earthquake shaking. Okay. Do we want that? Strictly no, because we have the possibility of cascading collapse of the entire building. Right. Then you have strong column, weak beam, the other one. What is the possibility here? Your column is not likely to fail before your beam. Okay, the beams will undergo failure first. So your overall frame, overall structure is not going to come down. You have low level beams getting distress damaged, but your overall structure will keep on standing. Okay, so this is desirable. So you should always go for the weak beam, strong column design. Okay, so and repeatedly again and again we all talk about. So just to make you understand type of frame building only, for each member or the which component you want to make weak, which component you want to make it strong. Once you decide that, then everything falls in place. So that hierarchy is very, very important. Then we come to the famous chain analogy. Okay, since we have two types of failure, one is the brittle failure, one is the ductile failure. As we have seen from the earlier slides, your ductile failure is desirable, brittle failure should be avoided. So now let us take a chain. You have most of the links are brittle in nature, and an intermediate one is ductile. So this is the undeformed chain. So we have made the chain in such a way that the materials are brittle and ductile accordingly. So now when you pull the chain, right, the ductile link will get stretched because it can take large deformation. These brittle links they will not eat because they are capacity. But then after a certain point of time, they are going to fail. Okay? So the yielding or stretching will be mobilized or concentrated only in the ductile link. So now, when you look at the ductility of the overall chain, so you had some brittle components, we had a ductile component. And now, if you want to see that the ductile behavior of how it is utilized, so there are two possibilities. One is the weak link is ductile and the strong link is brittle. Okay. Now you are sequencing which one you are making, which one you are making. So first process you are making the brittle so what will happen? The ductile one will get stretched. The brittle ones are seeking force, right? They are not going to fail. Okay. So the overall chain gets stretched, right? The overall chain gets weak link is the brittle and the strong link is the ductile one. So if you look back to the figure, so these brittle links are the weak ones. So they are going to fail first, and the ductile link is okay. So that means whenever you are going to pull such a chain, your brittle links are going to fail first, and the ductile link will be intact. That is not going to fail. Okay, that will stretch, but then it will not fail. So one point to be clarified: when we are talking about failure of brittle link or brittle member, that means it reaches the peak strength and suddenly drops off. When we are talking of failure of a link, that means it's straight. For like the failure part. We are not saying that it is going to drop off after that. So once it goes into the inelastic part, we are saying that the ductile link has undergone failure. So it's not that the ductile link is breaking off or so. No, it's not that. If you try doing the same analogy, so you and leaves. Now, when the steel yields, we call that as the failure point of the under reinforced section. So it is not that the steel reinforcement bar breaks off or ruptures off. It gets yielded, so it gets stretched. Are you able to hear clearly?
Hello.
Is it audible
Yes, sir.
clearly?
Yeah.
Audible?
Yes, sir. Audible.
Okay, I'll continue.
Okay, sir.
Okay.
Oh, again. it is breaking.
The
Hello, sir.
is it breaking?
Yeah, yes, sir.
Okay, let me just
Yeah.
is it clear now? Hello.
Yes, sir. It is clear.
Okay. So we are talking about this under reinforced failure. So the steel reinforcement yields, okay, that we call as the failure point of under reinforced section. It's not that the steel bar breaks. So that similar analogy is drawn here. So the ductile link is weak. That means it gets stretched once it fails. So second possibility, as we mentioned, that the strong link is ductile and the weak link is the brittle one. So what will happen here? The brittle link are going to break off. The ductile link will remain intact, but then the ductile link has not failed. That means the ductile link was unable to get stretched. So the overall failure is brittle. Okay. So these are the two failure possibilities in case of that chain, right? So relative weakness and strength of the brittle and the ductile link will determine whether the failure of the chain is ductile or whether the failure of the chain is brittle. Okay. So now we properly. Okay. So that analogy just really at
Hello, sir.
the procedure.
Your voice is still breaking, sir. Let me call him. Sir, still your voice is still
Yes,
not
you can.
clear, sir.
Yes. I'm just checking the network. Possibly the
Okay,
network
okay.
is.
Yeah, maybe, sir. Just try to reconnect with the network.
Yes.
Yes, sir.
Okay. Uh, Is it clear now?
Yes, sir, it is coming.
It is better.
Yeah, it is.
Okay, let me share the screen.
Yeah.
So let us look at the procedure of capacity design. Okay. So what we do is the first stage, that conventional design has to be done. So as you know that in case of the calculation of seismic forces, design seismic forces, the base shear is obtained first, and then they are distributed at different levels, and then we do the analysis. So essentially what is done is we are not going to use the total elastic force for calculating the design force and moment. Whatever load we are going to apply, or the force we are going to apply, is not the elastic one, but it is reduced to get the nonlinear behavior. Because as we mentioned, we want the damage to happen at certain locations. So the elastic force gets reduced by that response reduction factor. Right? So that will involve more deformability. So whatever is the required strength of structure, that we try to assess. So basically this is part of the conventional design, what we do for our detailing. Then we do the design. Once we have the design loads, we apply at different levels, do the analysis, and then we do the design as per the code specified safety factors. We have already applied the load factors, and then we apply the partial safety factor for material to obtain the uh, dimensions and the detailing. Okay, so we have to choose that which are the elements we want to make weaker and we want to make stronger, right? So that will come in the next stage. Okay, but then primarily the dimensions and the other detailing requirements are first obtained using these, right? So we want to design or detail the ductile elements, the beams and the columns. We want to do that. So that is the step 2. So once we finish the conventional analysis and design, then we have to choose the desirable collapse mechanism. Okay, so there are two mechanisms what we talked about. One is your weak column strong beam, okay, also known as sway mechanism. The other one is your strong column weak beam. Okay. So your two mechanisms are there, and then you choose the appropriate ones. Once you have the columns becoming weaker, your uh, locations of damages, which are marked in yellow circles here, they are in columns, and then the entire structure is in the danger of collapsing down. But that is avoided in case of the beam mechanism. Okay, so this is good, and that we should finalize as the collapse mechanism. So that was the step 3. Once you finalize the mechanism, then we try to obtain the upper bound strength of the ductile element. Okay, so your building is similar to the chain. Your building has brittle elements. Your building has ductile elements. Okay, so uh, your certain elements are going to be weaker. Certain elements are going to be stronger. So accordingly, you have to fix the strength of the ductile elements, because the ductile elements are going to be the weaker ones. We want them to fail first. So the ductile elements have to possess that minimum strength. So the design and detailing of the ductile elements has the maximum importance, right? Because they are the weak ones. They are going to fail first. So once we have the strength of the ductile element and the detail, then we design the brittle elements. Okay, so there are all the components have to be designed, isn't it? Your both the ductile and the brittle elements. So based on the failure of the weak element, whatever that time force and moment is coming to the brittle element, for that we have to design, right? So why is it important? We want the weak uh, element to fail first. At the time of failure of weak element, there will be some bending moment, some shear force on the brittle element, right? So that shear force or the bending moment of the brittle element it will be taken as the design one, right? Earlier, when we do the conventional structural design, we were not concerned with this sequence. We were not concerned that one element will fail first, and based on that failure condition, we will design the other element. No, we were not concerned with that. All the elements were being designed at the same time. We are not concerned with which one to make fail first and which one to fail later. So that sequencing was not necessary. Okay. So when the ductile elements are going to be uh, undergoing that deformation, they are going to yield, they are going to fail. At that time, brittle elements should not fail. So brittle elements have to be designed under the forces and moment coming at the time of failure of the ductile elements. So the brittle elements need to be elastic. They should not reach their failure load. If they reach their failure load, the brittle elements are also going to fail at the same time. Okay. So this point is very, very important. When the ductile elements yield, the brittle elements should remain elastic. Okay. So as we are seeing, these circles are the locations of the damages. In earthquake resistant design terminologies, they are also known as plastic hinges. Okay. So some of you may be familiar with the term plastic hinge. Basically, what is plastic hinge? Plastic hinge is similar to what you have studied in plastic design or plastic analysis of steel structures. Okay. So typically when you have the elastoplastic behavior, you know that it reaches that yield strain or the yield strength and remains flat, whether it's stress strain curve or load deformation curve, it reaches a plateau. So elastic and ideally plastic. So a bilinear curve is there. So once it reaches the plastic regime, plastic plateau, what happens? The strength does not increase. The strain or the deformation or the rotation goes on increasing once it reaches the yield strain. Okay. So that elastoplastic behavior is similar to that increasing strain with no increase in strength. Okay. Now, why do we use the term hinge? So that is the genesis of the word plastic, because we are looking at that plastic condition. Why is it called hinge? Because if you recall the example of a door hinge, in the door hinge, what happens? You have the frame and the panel, door panel is attached by means of certain hinges, right? So ideally, if those hinges are frictionless, then with any push, small push on the panel will go on freely rotating. It is not supposed to stop, right? But then, due to the presence of friction in the hinges, if you push a panel, it will open or close, the panel will rotate, but then after a certain time, it will stop, okay? Because the frictional resistance is trying to impede that motion. So if you have that ideal case where you do not have the friction, the panel will go on rotating without taking any load. So that means the panel rotation is going on increasing without increasing the strength. Okay, so that is a similar behavior to that plastic regime. You do not have increase in strength, but with increase in strain or deformation. So that door hinge analogy brings that term hinge in that plastic hinge part. Okay, so when you study this plastic hinge failure earthquake design in detail, then you will know that. So anyway, these are locations of damages, and the observed failure modes are going to occur at those locations. So one of the points which we mentioned earlier was we have to select the locations of damages. So these are the locations of damages which you have to select first before you embark on the design. Okay, so these are the locations which are shown here. So in case of beam, what has been magnified here, you have the end shear forces and the bending moments at the generated after the damages happen. Okay, so if your beam is the weak element, okay, so the beam is going to have those damages first, and with the damages in the beams, whatever forces are going to come in the columns, which are the stronger ones, right? The columns are your stronger ones, because in the columns, as you can see, there is no such blue circle, right? So no damage has been observed in the column. So the columns are going to remain undamaged at the time of the beams getting damaged. Okay, so the beams are the weak elements, the columns are the stronger elements, right? So this is how you estimate the design force on the column at the time of the damage in the beam, right? So these were the steps in the procedure, 5 steps. Let us implement them and see, in case of a RC frame building, how you really land up with the capacity design. Okay. Also, we need to see that whether you need to carry out any reinforcement detailing to make it consistent with that. So before going to the multi-storied RC frame, let us relook at the basic behavior of a portal frame. Okay, so in portal frame, you are familiar with the locations of these plastic hinges, because for this type of frame you had already uh, studied to calculate the failure load when the plastic mechanism occurs, when the collapse mechanism is mobilized, right? So it's in a similar way only, no difference. So these hinges are in the beams. Okay, so first the damages will occur in the beam, that's what we want, and next the damages will occur in the bottom of the column, right? What is the alternative mechanism? Instead of the damages in the beam, both the sections of any column, whether it's the left column, whether it's the right column, both the top and the bottom sections are going to have the damages. So that's the example of a weak column. Okay, whereas this one is the example of a weak beam, because the beam is going to be failing first. Okay. So this is how the mechanism will occur in the portal frame. Okay. Then let us move to the multi-storied frame. So your superstructure will have the different components. Your beam column joints are also important, because as such we are not much concerned with the design of beam column joints. Only when we do the capacity design, earthquake resistant design, we really look at the strength of the beam column joint. Otherwise, in conventional design, we hardly look at the strength of beam column joint. We hardly do the design. Right. So these are the locations of the initial damages. The beams have got damage at the different floor levels as well as the roof level. Okay, and your bottoms of the column have also got damaged afterwards. Okay. But the sections in the upper stories of the columns, none of them is shown to have got damaged. Right. So your ground shaking was idealized into the equivalent lateral forces, and the conventional design was carried out. So these are the locations as we had seen earlier. Okay, why are we using the term omega, this subscript omega? As we will see, this is coming due to a particular characteristic known as overstrain. Okay, what is overstrain? As we had seen in conventional design, we had applied that gamma m, partial safety factor, in order to bring down the material strain. We are not using the actual strain, we are looking at the design level lower strain. Okay. Now, during the time of earthquake, your beam or column or slab and the overall building, none of them knows what is safety factor or anything. Whatever material is there, it is going to behave as per its actual strength, right? So actual material properties are going to get mobilized during earthquake shaking. So whatever idealization or conservativeness we had brought in our design calculation, okay, that remains on the paper, but during actual shaking, your actual material properties get mobilized. So what will happen? Your partial safety factor for reinforced steel was 1.15. So that had brought the yield strength Fy to 0.87 Fy. Now what will happen? That 0.87 will go away. Your actual yielding is going to happen with the strength as Fy, right? In fact, as we will see in the stress strain curve, if you look at the reinforcing steel, if you look at the plastic regime, the strength does not remain at Fy, it further increases. Okay, so that increase in strength beyond the design level strength, that is known as overstrength, right? So what we ignored the actual behavior during the conventional design by bringing those partial safety factors, those are going to contribute to higher moment higher moment capacity, right? So when the uh, beams are going to bend under these lateral forces, assuming that the beam column joints are rigid, okay, the columns will bend in double curvature, the beams are going to bend in double curvature, just like you have a portal frame under lateral load, the columns bend in double curvature, beams bend in double curvature. So same analogous deformed shape will be observed here, and then the moments in the beam at the two sections, they will be mobilized as per the actual material properties. So whatever number of bars you have provided as per the conventional design, all those bars will develop that overstrain, right? The concrete will not have that partial safety factor for material gamma m as 1.5. That also will not be mobilized. It will have actual strength. So the actual concrete strength is higher than your design strength. So if both your concrete and steel are having that overstrength, obviously your moment of resistance is going to be more than the design moment of resistance. So mu limiting or limiting moment, what you calculated from that under reinforced design calculation, that is going to be exceeded. So this m omega is going to be more than that limiting moment of resistance, limiting moment or the design moment capacity. To have the equilibrium for this beam, that shear force will be based on this m omega, not your design moment. Because now during the to and fro shaking, your beam is going to have the moment m omega. So the equivalent shear, equilibrating shear force will also be based on m omega. So now this shear force is going to be more than the design shear force, what you calculated from the IS 1893 part 1 as part of that conventional design, right? So here lies the primary concern. During the actual shaking, you may land up with this shear force going to be more than the shear force what we have designed for. Okay, that can endanger the safety of the building, safety of your individual member, safety of the building as well. Okay. Let us move forward. So, as we mentioned, you have the reinforcement stress strain curve, steel reinforcement stress strain curve. Your actual characteristic strength is Fy. We had brought down to 0.87 Fy. This is the design level. And as I mentioned, if you look at the high yield strength deform bars, that means Fe 415 onwards. Nowadays, Fe 415 is becoming almost obsolete. Very less production is there. So Fe 500 onwards, most of the stress strain curves are going to have this increase in strength. If you see the regime, okay. So you may have strength almost close to 25% more than this Fy. Okay, so that's a pretty large amount, because if you look at the margin of how much strength we are ignoring, so basically 1.25 Fy divided by 0.87 Fy. So that is the margin what we are ignoring completely. Okay, so that is almost 40%, almost close to 1.4. So that much strength is going to be added up in your limiting moment of resistance or moment capacity when the actual earthquake shaking takes place. Okay, so that all will be going into that unsafe shear force, which for which you have not accounted for during the convention. On the other hand, if you look at the concrete part, okay, normally if you do the design of the reinforced concrete section flexural compression as per IS 456 stress strain curve, you have the 0.45 FCK, okay, and you have only your that partial safety factor and a single stress strain curve. But in reality, you have two possibilities of the stress strain curve of concrete based on the confining action. Okay, all of us know that once you have a column, okay, and the column is under axial compression and shear force bending on whatever, under the axial compression, your concrete of the column tries to bulge out. Now, the part of the concrete inside the transverse reinforcement, let us look at the figure here. So, if this is the tie of a column, so this inner concrete will not be able to bulge out because these legs are going to hold it. Okay, they are going to confine the concrete. So what happens? They cover concrete. Cover concrete can bulge out very easily. That fails earlier. Whereas this inner concrete, by virtue of confinement, fails much later. Okay, so that's why your mobilized compressive strength of this inner concrete is much more. Okay, so it is under vertical compression. It is held on all the sides by the lateral uh, confinement of the ties. So it is under triaxial compression. All the three directions you have the compression. Okay, so similar to what you have done in soil mechanics laboratory under triaxial stress condition, you had done the triaxial test under the hydrostatic pressure as well as the compressive stress. Your soil strength was mobilized to be very high as compared to the expected one. Here also, as compared to your 0.45 FCK, your confined concrete will have more strength, right? Even it exceeds sometimes FCK. Okay, not only 0.45 FCK, it exceeds FCK, the cube strength. Okay, so we land up with two possibilities of the stress strain curve under actual earthquake condition. So using these and the properties of steel for any section, whether it's beam, column, whatever, okay, your moment contribution, moment capacity is going to be high. So as we are going to make the beam sections weaker, they are going to fail first. So that M omega for the beam is going to be higher. So actual material properties are used, as we mentioned, the overstrength and overstrength is considered, and we are not considering the partial safety factor. So when you look at the analysis with the plastic hinge, since the beam is primarily undergoing bending, we look at moment rotation curve. Okay, when you will study nonlinear analysis, we'll see that moment rotation curve is an important characteristic which we try to give. Okay, so we'll not go into the detail, but your overstrength characteristic is illustrated by one such example. Okay, so now comes the important part. As we had mentioned that your beam section is now having uh, more moment capacity, that is going to give rise to more equilibrium shear force. So your total shear force in the beam will be coming one from the gravity load, the UDL on the beam, dead load, live load, whatever is there. Okay, so if small w is the intensity of your dead load and L is the span of the beam, we all know that at the two ends the reactions are WL by 2, and then you have the additional shear force coming due to these plastic hinges or the sections of the damages, right? So if you look at the IS 13920 provision, because when you implement capacity design in reinforced concrete structures, your Indian standard is going to be IS 13920 2016. So if you look at the figures of the shear design of beam, you get exactly similar ones. So there can be two possibilities. One is the beam bending in this configuration. Okay, this happens when you have the sway from left to right. If you take any frame and sway it either from left to right or right to left, whatever. So you have two possibilities. So your deform configuration gets changed, the signs get reversed, as you can see, and at the two ends, A and B, your gravity load shear and your shear due to the overstrength moment, they get algebraically added or subtracted. Okay, so at the two ends, you get the two conditions. So for the two cases of sway, you have two ends. So now you have to design the beam ends for this shear force, and especially when you have this plus sign, you may land up with a shear force which is more than the design shear force under the conventional design. So you have to recalculate your transverse reinforcement, right? You had provided the stirrups, the number of legs, diameter, all those you need to revise. Okay, so whenever you look at these figures of IS 13920, they are nothing but the implementation of the weak beam strong column philosophy. You have to first design the beams, the shear forces in the beam as the weak element, and then you have to recalculate. So this is the implementation of capacity design in IS 13920. So based on the failure capacity of the beam, you are going to design it as well as the stronger element column. That's why we call it capacity design, based on the capacity. Because when we are looking at the conventional design, we are looking at the design capacity with some partial safety factor. But here we are looking at the actual capacity. So the design term is gone away. We are not going to use actual. We are just going to use capacity design, right? So please remember that. So now, once you design the beam, what happens? These beams are framing into the columns at different story levels, okay, at the floor levels. So you have the beam column joint, which is zoomed here. If you zoom in, you have the shear forces and the two beam moments and the shear forces in the column, right? So what we do here is we have the points of contraflexion, that is points of zero bending moment in the column at the mid height location approximately. So at points of contraflexion, what happens? You do not have any bending moment. So if you take the free body diagram of the column and you try to see the internal forces or moments, then you get only the shear forces. However, since we are taking the free body diagram at the end of the beam, just at this location, okay, so your moments as well as the shear forces are shown. So this end of the column, top end and the bottom end are approximately at mid height, okay, for the column. So once you take this free body diagram, then what happens? Now your column design comes into action. You are basically interested to find out the shear forces VC, because we have already designed the beam. When the beams are failing, M omega was mobilized. At the time of M omega being mobilized, what is the shear force in the column? That's how our principle was stated, right? When the weak elements fail, what are the forces in the stronger elements? Okay. So when M omega is mobilized at the beam end, what is the shear force VC in the column? So for that, what we do, your frame member has this moment rotation property that depends on the axial force. When you are designing the column, you have this PM interaction also, right? So both these come very handy when you have the nonlinear analysis. In case of beam, only moment rotation is used because the axial force is neglected in case of beam. However, in case of column, the PM interaction comes into picture. Okay? So when you particularly magnify at this beam column joint, right, what you have is the overstrength beam moment. We already looked at M omega. And then if you take at the column section, at the end of the column, not at point of contraflexion, then obviously you have the moment capacity. Now here, your weak beam strong column has another check, right? So this is your design PM curve for column. So what will happen is your columns are not going to fail. isn't it? Columns are not going to fail. Your beams are going to fail because beams will have that m omega, but columns are not going to fail. So when you look at the design of the columns, okay, when you look at the design of the column, we use that familiar curve of SP16 when you are looking at the conventional design. So for the axial force, you have the overstrain moment demand for beam, right? Your design moment of column should be more than that, right? So when your beam moment is mobilized, m omega is mobilized, the moment in the column section, that means at this location as well as this location, they should be more than that. In fact, there is a relation given in IS 13920. We will come to that. But then graphically, it is being illustrated here that this curve, you pick up any curve from this SP16, which gives the design moment capacity of the column. So you pick up any curve for your column section, whatever is the design moment capacity of the column, that should be more than the m omega of the beam. Then only the failure of the column will be avoided, right? Your beams will fail first. So if you look at that provision of IS 13920, where you have the framing ends of the beams on a column, so again you have two possibilities, right? One is when you have an interior beam column joint, and the second one when you have an exterior joint. The exterior joint, you have the framing beam on one direction only. So you have the shear forces as well as the moments, just as it will come from any free body diagram. Okay, we are not showing the axial force in the column; they will also be there. So these are the important inequalities which need to be satisfied. So this summation of MC, right, of the column sections should be greater than equal to 1.4 times summation of MB. Okay, so these are illustrated here. So this ensures a 40% factor of safety over the sum of the movements of the beam. So when you look at this MB, basically they are the sum of the M omegas on the two ends, right? That overstrain movement. So those will be coming in case of MB. So this particular beam column joint moment inequality, that also reinforces your weak beam strong column. Okay. So these are based on actual capacity of the beam. So this is also part of your capacity design. So now our intention was to find out the shear situation of the column. What happens to the column shear force? Okay, so your column shear force is mobilized based on the same free body diagram what we looked earlier. Okay, so based on the overstrain moment capacity of the beam ends, you get the shear forces. Okay, this is simply from the moment equilibrium, all of you know. So this is again reflected from the diagrams in IS 13920. You have two conditions. One is sway towards right, sway towards left. Okay, so this one is sway towards right. Okay, when your beam is bending in double curvature. So on this side you have the beam going in the hogging configuration and then going into the sagging one, right? So you will have the hogging moment like this. Here you will have the sagging moment. So this is the sway to right. Okay. So under that condition, you can match the same nature of the forces. Okay. Now, in the previous equation for the beam, 1 point, please note that you have a factor of 1.4. Okay. What is the genesis of this 1.4? Your ratio of that 1.25 in that steel strength and 0.87, that 1.25 by 0.87 is 1.4. So the same thing is reflected. What is the underlying fact? In earthquake resistant design, in fact in all design, we have under reinforced failure. So the failure of reinforcing steel is going to be first before the crushing of columns. So your steel is going to reach that overstrength, large strength level earlier. So that 1.4 factor comes from that ratio. Okay. So this is how the 1.4 comes into picture. Same 1.4 is reflected in case of columns. So this 1.4, this is from that beam, that same beam equation, what we had seen. This is the overstrain moment. Okay. So basically this m omega is being expressed as 1.4 times the design moment. So this m subscript q superscript b h, this is the limiting moment of resistance from the design, okay, with at the point B or at section B under hogging condition. So these are the same figures of the shear design of column, and when you look at the equation, you get the same nature of equation what we earlier looked at. So again, this 1.4 factor is there. So all these are part of your capacity design, no difference. Okay. So all these are well implemented in IS 13920 at beam level, at column level for beam column joint. Okay. So once somebody follows IS 13920 in minute detail, he or she should be able to incorporate capacity design. This is not at all a difficult one. There is no major challenge here, but then the challenge comes only when you do the detailing, right? When you do the detailing. So the detailing part is very, very important. These diagrams are quite familiar with most of you, because whenever you talk about earthquake resistant design, we talk about this bent hooks of your ties in the column or stirrups in the beam as 135 degrees, because if you make them 90 degree, you do not bend inward, they are most likely to open up. Okay, so for cross ties also, for hooks, for main tie legs, we follow this 135 degree hooks. So nothing more to emphasize here. But then major thing to be kept in mind is when you do the ductile detailing of beams and columns. So what was our original keyword? Impart ductility at overall level, member level, section level, story level, everywhere. So you need to follow the reinforcement detailing also. So in order to achieve capacity design and ductility for both of them, you need to ensure the ductile detailing. So these are the figures for the ductile detailing. These are part of your capacity design as well. Okay. So as you can see, where you have the possible locations of damages at the ends of the beam, where you have the maximum bending moment, you are spacing the stirrups at smaller intervals. Okay. Whereas towards the middle part of the beam, you are spacing the stirrups at large intervals, so large gaps. Right. So these ensure that the beams undergo that failure through yielding of steel under reinforced failure. But when you are giving the transverse reinforcement in close interval, your shear failure is prevented, because you must remember shear failures is inherently brittle. Okay, because shear involves diagonal cracks and diagonal crushing. Right, any shear can be decomposed into diagonal cracks and diagonal crushing. So both are brittle type of failure, whether it's crushing, whether it's crack in tension. So those should be avoided. So your closer spacing of stirrups effectively confines the concrete, increases the shear strength, compressive strength as well as shear strength. So those are primarily to ensure prevention of shear failure. But your main reinforcing bars, the main longitudinal bars, they are supposed to undergo yielding. They are allowed. Okay. So the spacing of the hoops, the required diameter, and all those details, they all prescribed to capacity design. Next, when you come to ductile detailing in column, okay, because this is all part of implementation. Finally, your behavior will depend on how you have carried out the detailing. If your detailing is good in all the reinforced concrete members, your behavior is expected as desirable. Okay, so in the column also you have special confining reinforcement. As you can see, the ends of the beams, the ends of the columns. The ends of the columns are where you get the maximum bending moment in the column. Okay, so they are also going to be confined through special confining reinforcement. When you have the column going into a footing, The special confining reinforcement, the ties at close intervals, that is extended into the footing, as we see here. Okay, as we can see here, right? And then how up to which distance, how far you are going to implement the closer spacing depends on this L0. Then there are certain inequalities. So all these are given. Okay, so if these are implemented at site, the capacity design is being implemented. Okay. So all these are part of ductile detailing, and ductile detailing is very much necessary if you want to implement the capacity design. The calculation for the confining reinforcement is given by these equations. These are for rectangular sections. You have a similar set of equations for circular sections. Okay. So these are well established. Only thing, depending on the size of the column, sometimes the transverse reinforcement becomes very congesting. Congesting in the sense that you may have to use large diameter ones in order to have sufficient gap, because you should not have very small intervals between the two levels of ties, because when you are putting the concrete, once you pour the concrete, afterwards many of the places you still vibrate with a manual vibrator, right? So the needle vibrator or whatever needs to go inside the core concrete and get it vibrated properly. So if you are putting the legs of the ties, the spacing of the ties too close, too small, then your vibrator will not be going in. Right? So that is the major challenge, how to play around with these numbers. So anyway, once you solve an example, it will be clear. So these are all the implementation part, and I've just focused on the basic diagrams and figures so that the underlying concept is clear. Okay? So towards the closure, the main importance is the strategy to improve the ductility. Okay, so that is how your entire earthquake resistant design revolves around. Okay, how to make the structure ductile and strong, right? There are other characteristics required for overall earthquake resistant design. We look at the stiffness, we look at configuration. Probably Professor Hemant Kaushik must have told some of the points yesterday, and then these are the basic criteria what you require, and then you have to decide the collapse mechanism, right? And then increase redundancy in the structure. What is meant by redundancy? Your weak elements are going to fail. At the same time, brittle elements should not fail. So there must be enough margin, enough reserve strength in the structure so that it keeps on standing. It should not happen that the beams are failing and the columns are so weak that they are also failing at the same time. No, that should be avoided. So ductility and overstrength, they all play a major role in those things. Sometimes we observe that in the multi-story building, a certain story becomes weak. Okay, the other stories remain as such very well, but one of the stories has been so weak that it got collapsed. It's something to be avoided. It's not at all desirable. Okay. And then we all mentioned that the predetermined locations of inelastic action, they should be undergoing the desirable behavior. That's all. Okay, whatever behavior you are designing for, they should undergo. So to end with, these are some of the references, because Professor Hemant Kaushik suggested that some reference books should be provided. Already he has mentioned the books by Paul A. Priestley, Agrawal Shikhande, and Professor Duggal. So Paul and Priestley is the classical book from which all of us learned earthquake engineering and capacity design. It's very well discussed there. Overall earthquake resistant design and to some extent capacity design are present here also. Okay. So if you want to look at the solved examples in Indian context, the last two are the ideal books. Okay. This book came up in last few years by Professor Jack Moelly. So he has been a pioneer in case of earthquake resistant design of RC buildings. different types of elements and those things are covered. You will learn a lot if you go through this. Okay, so these are the suggested books. So before I end, I must acknowledge some people and the institutes. So first of all, I'm really thankful to the Department of Civil Engineering, Jabalpur Engineering College, for organizing this short-term training program, and gives us immense satisfaction that we are able to share some of the basic things, whatever we learned with the students, so that from your side also the questions and queries help us get enriched, right? Because many things what you think they are silly questions, please always feel free to ask. Otherwise it always becomes a monologue, one way interaction, so it doesn't help. So anyway, and particularly thanks to Vipin Tiwari, our former student, for organizing this. And then Professor CVR Murthy, who is in IIT Madras, he has been my supervisor for master's thesis as well as PhD thesis. So you must have noticed that many figures and diagrams I had written something referred to like Murthy 2003, Murthy 2001. So many of the photographs and figures I borrowed from him. So how to visually translate any concept into a very clear figure. Okay, because as all of us know that figures are very much informative and they teach us a lot. So how to draw figures and clarify concepts, that's something I tried to learn from him as much as possible. So many of the figures I borrowed from him, many of the figures during my days at IIT Kanpur, we made together. Like I tried to improve, he suggested more improvements like that. So anyway, so a lot of things I learned from him, technical, non-technical aspects. Then National Information Center of Earthquake Engineering, NICE. Many of you already must have heard about this. So a lot of information on earthquake engineering is available there. Please visit this website. And finally, the institute where I work for the last 11 years, IIT Guwahati, okay, is very much gratefully acknowledged. So thank you all for your patient listening. Slightly longer session, but anyway, I thought to clarify all the things.
Thank you, sir. It was very wonderful session. So, participants, if you have any question, you may ask. You can ask in chat box or unmute yourself and ask the questions. Sir, Vinay Gupta is asking what is difference between capacity design and performance-based design?
Okay, very good question. See, in performance-based design, what we try to see is that different elements of the structure, different components of the structure are going to achieve or going to perform at some pre-specified levels. Okay, like the rotation in the beam section should achieve a certain value, right? The story drift at a particular story level should achieve a certain minimum value, right? So there are certain performance criteria which need to be specified a priori, depending on the structure, depending on the requirement, that those are going, those should be achieved. Now, capacity design procedure is a mandatory one. So whatever structure you are going to design, you have to identify the failure modes, sequence them, establish the strength hierarchy, establish the weak elements, strong elements. So irrespective of whatever structure you are going to do, whether you are going to carry out performance-based design or not, capacity design is mandatory. It's a mandatory part of earthquake resistant design. So beyond that, when you are trying to establish a certain minimum performance level or a certain level of earthquake shaking, of course, return period of earthquake. So that is the additional top-up prescription on the capacity design. Okay. So in order, if you want to carry out performance-based design, capacity design has to be done mandatorily. Okay. In addition to capacity design, you need to see the performance levels corresponding to the actual behavior. Now, this statement is very easily stated, and if you try to achieve this, you encounter enormous difficulties because when you're talking about actual behavior, you never know that what exactly the actual behavior is going to be, because you never know the ground motion. There are so many uncertain aspects revolving around that. So we try to find out the actual behavior in two possible ways. One is try to build a small scale model and do some testing on shake table or some other way in laboratory. Okay, so that's obviously a scaled down version. Okay, and then try to map the behavior of that scale version onto the actual one, right? Second one is to resort to numerical simulation. So when you do numerical simulation, you are going to idealize the structure and a host of approximations are going to come into picture. How good you can realistically simulate the behavior of each member, each section, each material point, that's all your basic crux of numerical simulation is about. Because you can model anything, give some property, do some analysis, get some result. But then how realistic are those results? You never know. Okay, so both are extremely challenging. So performance-based design needs to be supplemented with these. So in performance-based design, once you set the performance level, you do the conventional design, you do the capacity design, you set the performance level, and then you do either nonlinear static analysis or nonlinear time history analysis, dynamic analysis, whatever you do under a suite of ground motions, different ground motions, and try to see the all possible variations in the behavior. Okay? And then see maybe statistically in how many of those cases the performance levels are not achieved. Okay, then you do some iteration, you try to change the design. Okay, but then your primary premises of the conventional design and followed by capacity design, they need to remain in place. Okay, so performance based design is one step ahead of that. Does it answer your question, or to some extent?
Vinay Gupta, you may unmute yourself and say something.
Yes, I may like to hear from him.
Yes, sir.
Okay.
Okay, no problem, sir. Sir, one more question is there. Sir, Faraz is asking, what is the possible location of plastic hinges in shear wall?
Plastic hinges in shear wall.
Shear wall, yes.
Okay. So the question is being asked by somebody who is already registered in this course, short-term course.
Yes, sir.
Okay. So I will explain in detail possibly tomorrow afternoon when I have the lecture on shear wall. But
yes,
let
sir.
me just show one of the figures. Yes, this one. Yeah. So this figure represents the shear wall along with the moment resisting frame in a typical multi-story building. So you must be knowing that the shear wall is used beyond say buildings of 5-6 stories like that till a certain level, because if it is very tall beyond 50-60 stories, shear walls become uneconomical. Okay, so when you look at the plastic hinge of shear wall, first of all, when you looked at the plastic hinge of the columns and the beams, we saw that they are at the end sections, whether it's the bottom section, top section of the column, or the left or right sections of the beam, right? We all know the reason, because in the portal frame diagram we had seen that under lateral load you get the maximum moments in the top and bottom of the columns, you get the maximum moments at the ends of the beam. Okay, so in shear wall again there are two categories. One is a slender wall, where the height of the wall, that means this height divided by the length of the wall, is more than 2 or more than 3. That brings the category of slender wall. If it is less than 1, it becomes squat wall. So the behavior is different. In slender wall, when you look at isolated wall, just like what is shown here, isolated wall with the lateral forces, say, coming from the story level. So here it bends like a vertical cantilever, right? Vertical cantilever with the bottom end restraint. So obviously your plastic hinge will be located at the bottom of the wall. Okay. So most of the design codes, not the design codes, most of the guidelines on your nonlinear static analysis, and when you try to model the material nonlinearity, plastic hinges, they talk about the location of the shear wall in slender wall, plastic hinge in slender wall at the bottom, right? But then shear wall is not really in an isolated standalone condition. Here we are showing it as a standalone. It is not connected to anything, only a single wall. But in reality, if you see the figure, the floor slabs as well as the roof slab are connected to the wall. Okay. So what happens when the shear wall tries to bend, whichever direction, it is restrained to some extent at the intermediate levels, also at the top level. So the slab is not permitting to bend it in a standalone vertical cantilever way. Okay? So what happens? Your inelasticity or the locations of damage, they get distributed at different locations, especially around these slab wall junctions at the different floor levels. We have seen earlier also damages have occurred, not only in past earthquakes but in numerical simulation also. So my first PhD student, Dr. Snehal Kaushik, she investigated this influence of the slab on the shear wall behavior. So she observed that your location of plastic hinge is not concentrated at a single location, unlike what is mentioned at the bottom of the wall, but around the floor slab region also you have plastic hinges. Okay? So for a slender wall, if it is connected to slab, you have the plastic hinge locations at the slab wall junctions as well as the bottom, right? So that is the answer. If it is a standalone vertical cantilever, only at the bottom section, plastic hinge, all the damage. Basically, plastic hinge is where all the damages can occur. So maximum bending moment is the location. If it is a squat wall, then it does not have the flexure dominated behavior, just like a deep beam. It has shear behavior, shear deformation. So in a squat wall, it is mostly the like a shear cracking, the diagonal crack and the diagonal crushing. Okay. So in squat wall, we really don't specify the plastic hinge region. We don't talk about plastic hinge.
Okay, sir, I just wanted to ask one thing. Like in while doing ductile detailing, there is
Yes.
a means where at beam and column junction, there is a length L naught you have shown in the diagram. For that, we reduce the spacing of stirrups. So, how
Right.
do we decide that L naught? Is it related to the plastic hinge length or what?
Very good question. I'll just
Yes, here.
slide. Yes. Uh, you are very right when you're saying that this is the possible plastic hinge region. Yes. So whenever we look at the cracking of concrete in a column or beam, whichever, it is not a single section, one particular section where the cracking occurs. It occurs over a length of the member. So in the end of the beam also, when we looked at the ductile detailing in beam, we looked over a certain distance of 2D over which we have very close spacing of stirrups. Okay.
Yes, sir.
And when we look at the column, here also it is like over a region of L0, you have the very close spacing of the ties. So exactly this is the region where we expect the maximum cracking of concrete to occur, maximum damage to occur. That's why we are confining the concrete over this region with the help of closely spaced ties. So roughly, if you want to locate the plastic hinge, because when you do nonlinear static analysis, pushover analysis, where we really want to see the extent of damage or the damage location, there we can't model by means of different locations of plastic hinge. We try to provide a single location. So that plastic hinge location will be in somewhat mid region of this L0. So at some L0 by 2, we will model the plastic in section and do the analysis.
Okay. Okay, sir. Sir, one more question is there.
Yes.
Shen is asking, what in case of flat slab systems as there are no beams?
Right.
In case of flat slab system, sir, I
So
hope he's
what
asking
plastic
about
hinge?
the plastic hinge. Yeah.
Yes. So in flat slab, what happens is you do not have beams, you have only the slab and the column. So if I go back to one of the figures, same figure as the wall. Yes. So here, what you don't have the beam and you have only the column. So the failure mode in the slab is primarily concerned with the punching shear. Okay. So in flat slab, punching shear is the primary failure mode in the slab. Whereas in case of the column, the failure mode is similar. It can be in bending moment, it can be in shear, whatever. So in case of flat slab building, if you are modeling the plastic hinge in case of column, it will be at the same location, that L0 by 2, L0, whatever, at the ends of the column, top and bottom, for every story. In case of slab, we don't model the plastic hinge. We don't give a plastic hinge section. What we try to do is, we try to give the slab property or model the reinforcement in some smeared model instead of discrete parts. It's not possible, very difficult for an entire building. So in those cases, we do not assign plastic hinge. Directly from that nonlinear material property, what we assign, we try to see what are the strains and stresses in the slab reinforcement, whether the stresses in the slab are such that punching shear is likely to happen. Okay. So in flat slab building, again, the problem is your columns should not fail first. That is the primary thing. So your slab should be comparatively weaker. That's what we exactly look at. So it's like weak slab, strong column type of system, because we do not have beam. But then that is also not very desirable, because if the slab collapses even over a smaller areal extent, that's disastrous. So in flat slab building, we really have trouble in case of severe earthquakes. So nowadays, actually, flat slab buildings are not at all recommended to be constructed in earthquake-prone regions. Okay? But if you look at plastic hinge locations, same as for the columns, as we have seen for the RC frame building, but for flat slab, we do not provide plastic hinge section.
Okay, sir. So thank you very much, sir. I think there are no more questions are there. So
okay.
Thank you, sir, for this wonderful session, and see you in the next one. Yes, tomorrow.
Okay.
Okay, sir.
Thank you so much.
Thank you.
Thank you.
Sir. Thank you.